everyone. So today we have Trygve Poppe from Norwegian University of Science and Technology, going to talk to us about an introduction to flow categories. Thank you.
Okay. First of all, thank you for having me. This should be fun. I'm going to talk about flow categories today. In the symplectic community, they're kind of a new hot thing right now, even though they were introduced in the 90s, but like they're coming back now. So I'll try to tell you about them, mainly because I think like the reason I think it should be interesting is that now we have like a good notion of homotopy theory for these objects. So maybe they are now like interesting also if you don't care about symplectic topology, just purely from a homotopical standpoint. And there are certainly lots of questions and problems where I think we would need more homotopically minded people to kind of help out solve some problems in symplectic topology now. So hopefully you will be inspired by this to join that. And this is like an expository talk. This is not my original work at all. It's based on one paper by Porcelli and Smith, which I can highly recommend as like a gentle introduction to flow categories. And then by the kind of big mastodon, the foundational paper, which is Foundation of Floer Homotopy Theory by Abouzaid-Blumberg. So I'll get right into it. Maybe this is like bad mojo, but I'll get right in with the basic definition. So a graded flow category is something which has some objects, like a set of objects. And this set of objects has a grading function on it. I'll denote that with this absolute value. And for each pair of objects, we should specify a compact manifold with corners, xpq, with dimension given by some of these gradings. And we want some compactness condition. I'll get back to why this is important later. The main thing to take away is like this equation in yellow here, which is saying that the boundary of xpq is given as a union over all other objects as xpr times xrq. And so as you might see, I've kind of crossed out corners here. Turns out that manifolds with corners are kind of not well behaved enough. We need something a bit stronger to get the good theory. So we'll talk about manifolds with faces instead. They are manifolds with corners that have a particularly nice combinatorial structure on the corner strata. And it's basically this nice combinatorial structure that allows me to make completely sense of an equation like this. A manifold with faces should have this property that a k-dimensional corner strata is uniquely determined by being the intersection of k codimension 1 strata. So like every codimension k strata has like an address, which is given by exactly which codimension 1 strata does it belong to. And as a counterexample to this, you can think of this teardrop space in 2 dimensions, because like at this little corner point here, we have a codimension 2 stratum, and it only meets one codimension 1 stratum going around here. So that's no good. But what having this extra structure of faces allows me to do is to specify the full corner stratification of X by giving you a formula like this. Because now it's pretty clear that, okay, yeah, these guys are again going to have some corner stratification, and that should now fully determine like the deeper strata of X. Right, so again, inside something like this, I would have xpr times maybe some xr r prime times xrq. And this is going to belong to exactly 2 of the spaces like this. So then that specifies one of the codimension 2 strata. And all the deeper strata are specified exactly like this. That's what I'm saying. This compactness condition is important because it gives some directionality, and we'll see in a moment why we want it. But first, let's do some examples. So the main, or like the easiest example to get to is in Morse theory. In general, whenever you have a Morse function on a smooth manifold, you can produce a flow category where the objects are the critical points, and they are graded by the Morse index of the critical point. And then all these manifolds that appear in the definition, they are the moduli spaces of flow lines that connect to critical points. So I thought I'd just do one small example here. And because it's Valentine's Day soon, it's fitting with this heart-shaped sphere, which has 4 critical points. The degrees of some of these guys, the degree of P, for instance, is 2. R lives in degree 1. And we have this Q in degree 0. So now we can try to identify some of the moduli spaces of flow lines here. So between P and R, there's only a single line, which is this guy. So we have like X, P, R is a point. Between R and Q, we have 2 points. So X, R, Q is a 0. And as I've kind of tried to draw here, we have a whole one-dimensional family of flow lines connecting P and Q. And their boundary is precisely given by this S0, or rather, it's given by this S0 times this point. So just in this very small example, we can kind of see how a Morse function gives us a flow category. But we can kind of ask, what's the point? Well, one thing you can do is that from having this Morse function, we can for sure extract like the Morse homology. For any graded flow category, you can cook up a chain complex. You can just take like the free abelian group generated by all the objects, and you can grade each object by the grading we had on the object. And then you can define a differential, which follows the normal setup in Morse theory by counting over the 0-dimensional moduli spaces. So when you have this equation down here, XPQ is going to be a 0-dimensional manifold, and you can count the number of points mod 2. And for this formula to make sense, you really want this compactness property, because if not, then you might have some infinite sum here, and that's bad. So that's why we have this compactness. But somehow it feels like a flow category has more information than just this chain complex, and that's exactly the point. Because we kind of know in standard Morse theory that the Morse function, it knows more than just the homology of the manifold, right? So okay, right here I did C mod 2 coefficients for an oriented, or even for any manifold, you can do a lot better by upgrading this to C coefficients. But still, the Morse function kind of determines a CW structure on your manifold, and it should somehow know more about the manifold than just its homology. It knows something about the cell structure. And for Morse theory on manifolds, we have all of these arguments like surgery arguments, the typical proof of the H-cobordism theorem. You can kind of move things around and argue by appealing to the ambient space. I mean, I can just pick a point here and I can kind of flow out from it and see that determines, I can actually access the ambient space that all of these things live in. In Floer theory, on the other hand, which can show up in many contexts, but in particularly in symplectic topology, you often have some kind of geometric setup, maybe some differential equation like a PDE that you would want to look at the solutions to. And the solutions, they form a flow category, basically. Okay, you have to do a lot of work to prove that they do some transversality, lots of hard stuff. But you can, in good cases, you can produce a flow category. But there it's like not the case that you can't actually argue about any ambient space. These PDEs live inside some huge infinite dimensional manifold, but that manifold doesn't have the correct homotopy type. That's not the homotopy type you want to study. It's like more linked directly to these moduli spaces of solutions. So you want some way of extracting information from this situation, like extracting invariants, by only looking at the moduli spaces. So of course, in Floer theory, one such invariant you could extract is the homology, and that's what's known as Floer homology, and it has been like the most important tool in modern symplectic topology, I would say, and also in other like flavors of low-dimensional topology. But we would really like now to extract more refined homotopical invariants just from looking at this flow category. And to do that, we need to introduce some kind of homotopy theory. So before we do that, let me mention some other key players. There are some very small flow categories that we can define. It's the empty flow category with no critical points or no objects and therefore no manifolds. And we can also have the flow category with one object and also necessarily with no manifolds. If we have a flow category, we can also just change its grading. I'll denote this with a little suspension, wink, wink. We just take the same objects, but we shift all the gradings up by n. And we take all the same manifolds. And like this makes sense now because here, like in the new grading, we have degree p plus n, we have degree q plus n, and the n's cancel out when we look at this type of formula here. So that's something we can define. Now to extract invariance, right? We would like to say that this flow category is well defined up to some notion of equivalence. For example, in Morse theory, you really want to extract invariance of the underlying manifold, not the choices you made to construct the Morse theory. So both the function, maybe some gradient, all of these should be choices that kind of don't affect the invariant you get out at the end. But they definitely, like changing the Morse function will definitely change the flow category. So we need some control here. Okay, we have a question in the chat. Yes, we consider negative dimensional things to be the empty set. And in particular, the empty set, right? It's allowed to be a manifold of any dimension. So yeah, so that in all of these formulas that we had on the first page here, for instance, like whenever R has kind of a grading where this would produce something negative dimensional, it's just empty. Yeah, so to talk about some notion of equivalence, we need the correct notion of morphism. And you might think that because these are called categories, we would want functors, but that's not what shows up in Morse theory. Instead, what shows up is something that looks more like a bimodule. So a graded flow bimodule, then you should specify for each point in each object of the source and each object of the target, you should specify one of these compact manifolds with faces. This time it has the dimension formula degree of p minus degree of q. So you've gotten rid of this minus 1, which might be familiar from Morse theory as well. And the kind of master equation for a bimodule is that the boundary strata of FPQ, the codimension 1 guys, they are labeled by the following two types. You're either kind of breaking at some object of y, or you're breaking at some object of x. So both this union runs over all the objects of y, and this union runs over all the object of x. And again, we have this condition that, okay, I'm saying that the boundary is this, but I'm meaning that like the full corner stratification of FPQ is determined by exactly these codimension 1 strata and their kind of natural intersection. So this, for instance, is what shows up when you have some generic one-parameter family of functions that's connecting to Morse functions. Then you can construct something like this. Essentially, what you do is you take your like one-parameter family and you add it to some very steep function like this that ensures that like all the flow lines can only go in one direction, and you look at the Morse theory of this function plus your family, and what you get out is some moduli spaces that satisfy some relationship like this. And a very important example is that if you look at these very small flow categories with only one object, then we can then see that, okay, this guy has one object, this guy has one object. So to specify a bimodule we just need to specify like a single manifold, f point. And that is not allowed to have any boundary because there are no other objects. So this has to be a closed manifold. And by the dimension formula, it has to have dimension n. And this also kind of shows us how we can take the disjoint union of two things. So if I have a bimodule f and a bimodule g, I can define a new one called f union g by just defining this to be the disjoint union of the manifolds. So far, so good. This gives us morphisms, but we also need some kind of notion of homotopy between morphisms. So that's what's called a bordism. So this, again, we have to specify for every object P in X, every object Q in Y, some compact manifold with faces. It has a dimension formula. This time we're doing +1. It should have this compactness property. And now the important thing of this definition is this kind of master equation, which tells us how the boundary strata behave. And this time, again, we have something very similar to the bimodule thing, but this time we're also having two kind of different boundary strata, which are just given by f and g, the bimodules we're making a bordism between. So this is like it's a dimension one more than a bimodule, and it's literally a bordism between what you would expect. And maybe the best like intuition for this is that when you have these bimodules between one point flow categories that were just closed manifolds, then a bordism is literally a bordism between closed manifolds. So we've at least managed to absorb all the theory of bordism of manifolds into whatever we're doing. So that's a good sign. And in Morse theory, these bordisms show up if you consider two parameter families of functions. Maybe they should be like relative some kind of endpoint, but that, yeah. This is how you prove that your Morse theory your Morse homology is well defined. And like all of this story so far was kind of inspired by the proof that Morse homology is well defined. And this fits into like a bigger picture, which is maybe the first like slogan of how to think about the flow category, which is to say that the flow category is like a chain complex in some category of manifolds up to cobordism. They really look a lot like chain complexes when you look at them. So what's this comparison? A flow category X had a master equation of this type. So now I'm dropping some things here to make the notation less overloaded, but the boundary of the moduli spaces in my flow category were related to some kind of product of other spaces in the flow category. And if we try to port this over to the chain complex side, especially like if we like the proof that the Morse chain complex is actually a chain complex, it uses precisely this fact to say that if I take x times x, which should correspond to like doing the differential once, doing the differential twice, then I get something which is the boundary of a manifold, which means that it's like 0 in the cobordism. Like this term here is now 0 in the cobordism category because it is the boundary of something. So this is like the flow category version of d squared equals 0. And this continues. Flow bimodules, they look a lot like chain maps, and mortisms, they look a lot like chain homotopies. So really, you can really do a lot of arguments with flow categories by just thinking through how would I do this for chain complexes, and then writing down something that's a bit more complicated because there's a lot of notation, but morally, it's the same thing. Okay, so now we can define for two flow categories x and y. We can consider the set of bimodules between them up to bordism. And if I want to, I can actually get some grading on this by considering all suspensions of x as well. So I guess this is a definition slash proposition by Porcelli-Smith, which is telling us that bordism is actually like a well-defined equivalence relation here. And as an example, by what we saw earlier about what flow bimodules on the 1-point flow category correspond to, we see that if we do this, consider this set of bordism classes, we get exactly the nth bordism group. So the O here is for like unstructured bordism, no extra tangential structure, because the structure group is O. And this guy acts on every other set of bordism classes. I mean, if I have a closed manifold M and I have some flow bimodule F, I can just take FPQ times M. And because M is closed, this is not going to mess up the corner structure, but it's going to just change the dimension of everything. And then the like big theorem of the first part of Porcelli-Smith is that these, like all the flow categories and the sets of bordism classes of bimodules between them, they assemble into a non-unital category enriched in modules over the graded bordism ring. We call this H flow O. And so non-unital is a bit annoying, right? Units and flow categories are in general a bit annoying, and I will basically avoid them for this entire talk. I mean, I wish there was a better way, but the problem is that you would really like to say that the identity bimodule x to x has something like xpq is equal to x times the interval or something like that. But this should also degenerate, right? I would want the identity. I would want the identity on x p to be a point. And this introduces lots of problems with this definition. Like, to make these two guys compatible, we have to introduce some weird degenerations on the corner structure of this manifold. So they're a bit annoying. But you can make them work, but in the Porcelli-Smith paper, they don't write this explicitly, but we'll see it. Maybe they'll show up again later. Okay, now by the kind of argument, this analogy between chain complexes and flow categories, and basically running through the same proofs that you used to show that the Morse homology is well defined, you get a functor like this. So like now this is a good candidate, right? This is a category that is kind of more advanced than just chain complexes. It has some graded structure over the bordism ring, which is bigger than C mod 2. So this is good, but we can still kind of get back the classical invariants. But of course, we would kind of like to have something even bigger. A homotopy category is good, but to really do like everything you would want to do, we would want to upgrade this to some kind of infinity category. And I mean, because this looks a lot like chain complexes, and we have these graded modules as our home sets, you know, you can start to speculate, is there an infinity category which has this as its underlying homotopy category? And if so, then it wouldn't be too much to ask that be a stable infinity category. And that is indeed what we get. Now we're into part 3. Abouzaid and Blumberg, they construct stable infinity categories of flow categories. So in particular, we have this flow O that has graded unstructured flow categories. And roughly speaking, I mean, H flow O is the homotopy category of this guy. Not on the nose, but I'm pretty sure you can make this happen. So how would one go about constructing such an infinity category? Well, the way Abouzaid and Blumberg do it is that they start by constructing a functor of monoidal categories from a category called manifolds with corners O to a category of posets. So what's this guy? This guy has these manifolds with corners as objects, and the morphisms, they're very strict. They're not like any smooth map of manifolds. They're only these strata inclusions. So if we go like all the way back to the start, we can see that to define a flow category, we're not actually thinking about any like smooth map of manifolds. We're actually only saying something about inclusions of boundary strata. So that's the morphisms that are allowed to show up in this monoidal category, and the product structure is just the product of manifolds. And then you construct this category poset, which contains only these nice posets, the ones that model the stratification of a manifold with faces. So this is how you can control, make sure that you're only seeing these manifolds with faces that you want to see. This category of posets, this should be the kind of natural home for your master equations. So any type of master equation, like the ones we see on the left here, these we should be able to write down as some kind of object in this category poset. At least as soon as you specify like the set of objects in X and the set of objects in X and Y, then there should be some natural poset which encodes all of these relations. Then you have some work to do, because I guess we're trying to construct this category of flow categories as some kind of simplicial set. So you need to say what are the n-simplices, and to do that, you're now trying to write down some kind of master equation for an n-simplex as some kind of object in here. And then once you've done that, you can define a flow n-simplex to be a category enriched in this monoidal category that maps to the correct thing down here. I mean, that it should, when you map down here, it should satisfy whatever master equation you were able to cook up. And if you do this correctly, you should get out at least a semi-simplicial set, which is your category roughly. Again, units are annoying. If you have this kind of enriched category, you're only allowed to pass to a subcategory. You can't, there's like no canonical way to enlarge this to a bigger category, which would be taking a degeneracy. You're only allowed to restrict. So this gives you a semi-simplicial structure. So mainly, like constructing the correct version of this category to get it to encode like, there goes my screen sharing. Let's see if we can get that back. Okay, can you see my screen again? Good. Constructing like the correct category of manifolds with corners that encodes the correct tangential structure, that requires writing down a lot of coherency and a lot of definitions, and it's a bit annoying. The definitions in Abouzaid-Blumberg get very large, but it's doable. And then you have to be kind of clever to write down these master equations for the flow simplex. But what you can do is that you can kind of take the normal n simplex and you can try to consider a Morse function on it where the flow lines like all go in the positive directions of the simplex. Right? I could have like all the flow lines go like this. And if you look at how the corner strata of such a Morse function have to break, then you can probably try to see from that what the correct master equation is. So let's try to see what it is in the case of a two simplex, which is like the next one up. First of all, to specify two simplex, I have to specify its boundary. The boundary should consist of, okay, a flow category at this vertex, a flow category here, a flow category here. I should have the flow by modules along the border. And now the question is, what should this guy satisfy? What kind of object is this B in here? So to specify B, I have to specify for all objects P of X and all Q in objects C. I have to specify BPQ, which is now again one of these manifolds with faces. And the dimension formula should again be something like dimension grading of P minus grading of Q plus 1. This is kind of happening at the same level as boardisms from before. But now the corner structure is going to be a bit different, because like at one end of this boardism, I can think of this as like a boardism going in this direction in the simplex. So at one end, I have just a normal flow by module. But at the other end, I have these two, like a composite thing, which is not quite a bimodule, because we haven't said how to compose them yet. But the way to deal with this is to have like this type of corner strata. So for every R in the objects of Y, you have some kind of half composed version of f and g. So like roughly the composition of f and g corresponds to looking at all of these guys, but if you just take this collection on its own, that's not good, because this union is not going to be a manifold with faces. It can look kind of like this. It's gonna have like this would be okay if it had if it was a filled in corner. That's okay. This is allowed to be a manifold with faces. But this product down here, it looks more like just this part. And that's not a manifold with faces. That's something more stratified, or yeah. But like if we allow that to be an object, then we can basically say that the two simplex is a boardism between this composed guy that maybe doesn't actually exist and H. And I'm writing the relative tensor product here, and that's like, there's a good reason for that. I mean, we are essentially taking just the product of all of these guys, the product of all of these guys, but we're enforcing that they kind of have to, we're gluing them along Y. That's why this object has to match this object. And in fact, if we could write down an object like this, then that would be great, because this gives rise to like a theory of Morita categories. If I have some kind of bimodule, like over an algebra, for instance. So say I have a bimodule B, and then I can try to compose that by another bimodule by forming their relative tensor product. And this is how you can define these Morita categories of rings or algebras by taking this to be your composition. And this also works for categories. You can define Morita categories where the objects are categories and the morphisms are bimodules between categories. But to define composition, you have to be able to define this relative tensor product. And to define the relative tensor product, you need to have colimits. And this is like the main difficulty, is that this category of smooth manifolds and strata inclusions, it does not have colimits. Precisely because of this problem, right? Here I'm trying to glue something that is a manifold with faces and something that is a manifold with faces along some kind of common part of the boundary strata, and the result is not a manifold with faces again. But if I could do this, I could say that this category of flow categories is like taking the Morita category of this guy and then localizing it, like inverting Bordisms. That's kind of another big brain slogan for flow categories. Right. And using a technique like this is also how Porcelli and Smith are able to construct this homotopy category of flow categories by saying that, okay, whenever I see something like this, you've kind of built in enough data in your objects that you can find a unique up to Bordism smoothing, so that like this new edge, this new thing here is now the composition of your two, and there is some kind of Bordism between them, witnessing that you were able to cook up this composition. Okay. This is the wrong page. Yes, this is better. Right. If we were now able to successfully carry out this little program here of writing down a master equation for all the n-simplices, we would get a semi-simplicial set of flow categories. And by doing this type of argument again, but keeping track of a lot more coherency, Abouzaid and Blumberg, they're able to show that this semi-simplicial set, it has horn fillers. So in the sense that if there's like a semi-simplicial I horn that lives inside the semi-simplicial delta n, and I can lift like this whenever 0 less than I less than n. So this is like the semi-simplicial analog of a quasi-category. That means that it models something like a semi-category, like a non-unital infinity category. What they then show is that this admits some objects that really look like units, that behave like units with respect to the composition. Objects that are kind of neutral when you see how they act on mapping spaces by composition. And this is a general principle that shows up in category theory, which is that as soon as you have defined the compositional structure of a category, then having units is a property and not extra structure somehow. It's like, then you can actually sit down and check and ask, does each object admit a morphism that is neutral under composition? And if the answer is yes, then there exists some kind of category that forgets down to your semi-category. This principle has multiple incarnations in higher category theory, For instance, the theorem that Abouzaid and Blumberg use is a theorem by Steimle. He gives a precise condition on a semi-simplicial set that satisfies these inner Horn fillers for when you can upgrade to a simplicial set, to a quasi-category. Another incarnation is the work of Harpas on quasi-unital Segal spaces or semi-Segal spaces, which is also, there's the same thing happening, right? That defining the compositional structure is one thing, and then it's a property to have enough units, to have enough like invertible things. Anyways, Abouzaid and Blumberg are able to show that this semi-simplicial set flow O has this property, and so they cook a infinity category from this. Now, as I kind of hinted to earlier, we want to show that this flow O is actually a presentable stable infinity category. This shouldn't be, like, the reason we're expecting this is that the category looks a lot like chain complexes. So let's see why this is reasonable. So first of all, the empty flow category is the zero object in this category. Why does that make sense? If we think about it for a second, what does it mean to specify a bimodule, for instance, like this? Well, then I would have to specify for all objects P in this guy and all objects Q in this guy some manifold with faces. But there are no objects in this guy, so that's a completely vacuous statement, and there is like no data required to specify such a morphism. So like the only thing you can put here is the empty bimodule. And similarly for like any higher simplex, if you have the empty guy at one of your corners, you're actually forced to put the empty end simplex. So yeah, that's a zero object of your category. You can take disjoint union of flow categories by taking disjoint union of their objects, and this gives you all co-products in the category. This is again a place where this compactness condition shows up, which makes sure that a big disjoint union is actually a co-product and not the product. So that's important. Again, this is related to this thing that you want finite sums and not infinite sums. That's sort of the difference between infinite products and infinite co-products, right? Furthermore, this category has co-fibers, and we can define them in a way that looks a lot like how you define the cone of a map of chain complexes. So given a bimodule F, I can construct a flow category CF, which has as its objects the objects of X, but suspended once, like I just increase the grading, union the objects of Y. And to specify my manifolds, well, I just pick, like, only one of these will be defined at most. And if none of them is defined, I take the empty set. So, right, so in this case, the grading formula would be something like the degree of P in X plus 1 minus the degree of Q in X minus 1, which is good, because this is also the degree of P minus the degree of Q, which was the dimension minus 1. Okay, yeah. There's even one more minus 1 on this side. This was the dimension of XPQ. And you can do this going down the list. And of course, at this point is where you will see that you're picking up one object from X, which has been suspended once. And you're picking up one object from Q, which has not been suspended. So the dimension formula is this. This is like what we would expect the dimension to be in a flow category. And now I cancel these ones, and I see that this is P minus Q, which was the dimension of FPQ. So this is okay, but I had to introduce this suspension. And okay, so it's a little bit tricky to show that this is actually the cofiber, but if you find a sufficiently like object-free proof that this is a cofiber in chain complexes, then you can try to generalize that. So the last part of presentability is then now we have cofibers and we have arbitrary coproducts. That's enough to get all colimits. So to be presentable, we just need to find a set of generators. And in fact, we're in a very, very nice situation here where the flow category with one object generates. And this is maybe not so surprising, because if I have one, then I can construct its suspension, its arbitrary suspension. And if I have like any flow category X, I can try to write this now as a kind of iterated colimit by just iterating over its objects. So at least if X has finitely many objects, I can start at the objects in the highest degree, and you can really build X object for object out of categories like this. So this is actually even nicer than being just a presentable category. We're generated by one object. That's precisely the condition in which the Schroeder-Shipley theorem holds, which tells you that when you're generated by one object, then if you can calculate the endomorphisms of that object, you can actually identify your whole category. So the big theorem is that the endomorphisms of one, that's the Thom spectrum, MO. I write conjecture here because it's not explicitly shown in Abouzaid-Blumberg, but I think it's very clear how to extend the methods that they do there. And this is not surprising, right? If we remember this one that we had in the H flow category, this was the Bordism ring. And this Bordism ring is precisely the pi zero of this spectrum by Pontryagin-Thom. So by doing a kind of space level Pontryagin-Thom argument, you can cook this equivalence. And as a corollary of this conjecture, you would get by the Schroeder-Shipley theorem that if you consider mapping spectra in the category flow O with their MO module structure that you get by composing on the left with an endomorphism on one, then you actually get an equivalence of categories. And maybe I'll mention that the version of this that they prove in Abouzaid and Blumberg is for framed flow categories. So that means that every time I said manifold with faces, you should instead say stably framed manifold with faces. And you should make all of these boundary inclusions and all of that coherent with respect to this framing, lots of coherency to write down. But in the end, you get that because the framed Bordism ring, well, that's just the homotopy groups of the sphere spectrum. Then if you try to run this like space level Pontryagin-Thom argument, you get that the endomorphism of the unit in this category flow framed is the sphere spectrum, and so you get this equivalence. So maybe that's like the final slogan of today, is that flow categories, they kind of categorify the Pontryagin-Thom correspondence to give you lots of equivalences like this. And I think you can cook a lot more infinity categories or flow categories with kind of any tangential structure that you might want to see. and you can get out a stable infinity category, and you can identify it with modules over some Thom spectrum. I think you should be able to do that. And I think that's it from me. Thank you.
Thank you very much. Is there any questions?